Thank you. Thank you especially to the organizers of Compose. I'm really happy to be here. So this talk that I'm going to talk about, it's based on some work that I did with these folks, Simon, PJ, Richard Eisenberg, and Dimitris Vitiniadis. Last fall, we wrote a paper called A Reflection on Types. And we wrote this paper in celebration of Phil Wadler's birthday. This is something academics do, is they write papers as birthday presents. But it's a fun paper, so I wanted to present it for you today. And if you want to know a little bit more details about what I'm talking about, you can find a copy of this paper on my website. Okay, so this paper and this talk, I'm going to talk about dynamic types. Specifically, I'm going to talk about a library in GHC that's called data.dynamic and kind of what its design is, because that's in flux, and how to implement that library, right? So first let's kind of look at what's in this library, right? So there's a type, it's called dynamic. And what this library does is allow you to do dynamic typing in Haskell, right? So we have a function for taking any type of value and forgetting its type, right? We're coercing it to type dynamic so the compiler doesn't know what type it has. And we have another function. Oh, yeah, here's an example where we can create this heterogeneous list. We can have characters and numbers in the same list by just using this toDyn function, by coercing them to have dynamic type. Then we can come back, right? We can say, if you have a dynamic value, let's do a runtime check and see if it happens to have the right type that you wanted. Right, and so here, and you probably noticed that we have these two constraints for typable. I'm going to get into those constraints because that really, actually, the design of typable really influences how dynamics work. And that's what I really want to hone in on. But what's going on here is the fact that we have these constraints. That's marking the fact that we have to do something runtime involved with types. Now, of course, maybe you saw the title of my talk and you're like, dynamic typing, you know? Why are you talking about dynamic typing? You know, and if you've seen me give other talks, I don't often talk about dynamically typed languages, right? For me, more types the better has usually been the story, right? Right, but here's what's going on, right? Your type system's a tool, right? And it should let you write the programs that you want to write. And some of those programs you can completely enforce through static type checking, and some of those programs require some dynamic checks. Or maybe you're a little lazy and you don't want to get everything, do all the proofs. That's okay. I want you to have the choice, and I want that choice to be available to you in a typed language. Now, why in a typed language? Well, of course, when you're on this side of the spectrum, I want it to be easy. And I want the language to really support your programming. But if you have to do some kind of dynamic checks, I want it to be possible, maybe not that easy. Okay, so let me go to an example of where you could use a dynamic type, right? So this is an example of where you really do need to, you just can't write it very well without it. So I'm not going to go into all the details, but say you're writing the ST monad. So this is a state monad. I don't know where to point in this room. Again, this is the widest room ever. Right, so we have a monad that is going to keep track of some state for us. Right, and working with that monad, we have a type of references. What do we want to do? We want to be able to, when we're in that monad, we want to be able to allocate references, but those references are going to be to values of a particular type. So the A parameter, this type parameter, talks about what type of reference this is. It's a reference to a value of type A. Right? And so if you have a reference to a value of type A, you can read from it. So the state monad will give you a value of type A by reading from that reference. And if you have a reference to a value of type A and you have a value of type A, you can update that reference. You can write to it, right? And the state monad just gives you units because there's no result from writing. There's this S parameter. I'm not going to go into it, but the S parameter is key because it forces the fact that you can't confuse your references together. And so once you've created something in the state monad, as long as you've used the S parameter parametrically, the run ST will let you run that monad as if it was pure code. Okay, so we want to implement this. This is built into GHC. We want to implement it. How are we going to implement it? Well, we need some place to store that data, right? We're creating references. We need to store to those references. We need to read from those references, right? What kind of store are we going to need, right? We need some kind of universal store that can hold anything, right? Back on this interface, right, we didn't want to say, okay, this is a ST monad that can only store these types, right? We didn't want to nail that down. We wanted people to choose what types they store. Now, this is a completely safe interface, right? Right, you know that if you have a reference to an A, you're going to get an A back. But we don't want to limit what kinds of A's that you're using. Right, so here's how we can use dynamic to implement this store, right? So our references, right, they're just going to be numbers. They're just going to be, you can think of them like heap addresses, right? They're just going to be indices into some map of values, but that map, right, the range of the map is going to be dynamic because we want to be able to store any type there, any type of value, right? And so when we extend that store, well, okay, we just coerce the value that we're given to have that dynamic type and insert it into the map. And then when we look up from that store, right, we look up from that reference, we're going to get something that has a dynamic type. And so then we have to do that check to make sure that we got the right type. Now, as implementers of our ST monad, we have an invariant, right? We know that when we allocate references, we're only going to allocate one reference for every type, right? We're not going to have reference 3 be to both map to both booleans in one part of the program and ints in another part of the program. That's going to be an invariant of our implementation, right? And if that invariant is true, then we know that this runtime check will never fail. But the type system doesn't know that, right? And so dynamic gives us a way so that we don't have to express that invariant in the type system. We can just check that we've always maintained it at runtime, right? It's a little bit of laziness, but it gives us this implementation. Okay, so that's how we can use dynamic. Where does it come from? How do we implement it? Right? I said, we have this library, data.dynamic, right? Can we implement that sort of thing? So here we can implement this universal store. Can we also implement dynamic? And so here's a very traditional way of implementing a dynamic type, right? What is it? It's just, well, we just have a constructor for every type, right? So if we want to coerce an int to be dynamic, right? We have a constructor for ints. If we have a dynamic value, that runtime check is just checking the tag, checking what constructor we have. We see, I'm expecting an int, right? Let's look and see if I have the dint constructor. If it's there, I can return it. If not, that runtime check fails, right? So, great. What's wrong with this implementation? Right? Well, the first part is it's only these types, right? And we wanted it for all types. So it's not an extensible implementation at all, right? It's whatever we put into our data structure, right? And maybe we only wanted to talk about these types, but in our example that we just saw, we wanted to talk about lots of types, right? And here's the other thing, right? So let's look at pairs, how we're treating with pairs, right? So again, we have Okay, so we have a way to take pairs and coerce it into dynamic, right? And so, but notice how two-dyne pair, right? It takes two arguments that are dynamics. What else could it take, right? right? We don't want to have, okay, here's a constructor if it's a pair of an int and a bool. Here's a constructor if it's a pair of an int and an int, right? So we just make it take dynamics as arguments, right? And then so two-dyne pair to create a dynamic pair is easy. Here, dyne first, this is working with a dynamic pair. So this kind of combines in, you are doing a runtime check to make sure that it's a pair, and then also extracting the first component at the same time, right? So maybe you will get a result if the thing happened to be a pair, right? This might be something you would want to use if you have a dynamic pair. But again, there's a little bit weirdness going on, right? If you have this pair of two numbers, how do you turn it into a dynamic value? Well, first you have to coerce 1 to be dynamic, then you have to coerce 2 to be dynamic, then you have to coerce the whole pair, right, with two-dyne pair to be dynamic, right? That's kind of annoying, right? Why don't we just do another approach where we just tag it with that type from the beginning? And so that's the alternative definition. So this is kind of the straw man approach, but here's what I think really should happen. Right? So this is data.typable. We're going to use data.typable to implement that dynamic type that we saw before. And what data.typable does is it provides runtime representations of types. Right? So let me talk a little bit about what's in how these runtime type representations work. And with a caveat that this is kind of a new interface. This is the code that I show you is not yet available in data.typable, but it's something that is enabled by GHC 8 that's going to come out next month. Right? Okay, so what's in data.typable? We saw the typable class, and that class has indicated that there was some runtime type representation. Right? So here it is. Right? So we have this type, capital T, capital R type rep. Right? This is the type of some runtime information. And the only thing in this class is a way to access the representation for that type. Right? So if you say, okay, I would like the representation of the type int, right? You write a type signature down, and then you can access, this is the representation of the int type. If you have the type int arrow int, right? It works exactly the same way. Unlike normal classes, though, this class is special. Unlike normal classes, you have representations for automatically. You don't have to say, please, here's the instance of this class, and here's what I want to use as the representation of the int type. GHC will automatically provide those classes, right? And that means it's completely extensible. Every time in your code, if you define a new type, you make your new data type for web pages, you get a type representation for web pages, right? The other thing to note is that it's indexed, right? So notice how the type representation, the class typable A only contains the type representation for A, for the type A, right? And so when you look at a type, right, if you look at one of these type representation types, you know what type you have. Right, that index makes this really tight coupling, right? If you see here, I have this value. I tell you it's the representation of int, but you don't have to believe me because you can look at that type. And then here's the last thing about it: it's polykinded. So what does that mean, right? So in Haskell, there's lots of different kinds of type constructors, right? So we have regular ones that like int that have just kind type, but we have parameterized type constructors that take arguments, like list or arrow. So arrow creates the function type if you give it two other types, right? And so there's nothing special. We can make a type representation for arrow, and so we're using the fact that we can have type classes that work for different kinds of types as well. And GHC knows how to, if we have a type representation for an arrow type, and we have a type representation for int, put those representations together to get this representation for this int arrow int type. All right, so it's going to construct representations for any type that you might write down by generating representations for the primitive constructors for you. we have type representations. We want to implement type dynamic. How can we do that? Right? So here it is. Right? So to create our dynamic type, we're just going to pair a type representation with a value of that type. Right? And so this data type definition, this is it's usually called an existential data type, right? And the reason is because we have this type variable A that doesn't appear in values of that type, right? So we're hiding this type A, right? And so what that says is we can create dynamics out of anything that we can create a representation for. But that's everything. Right, and so toDyn, right? toDyn just says, I'm going to create a dynamic value by hiding the type A, by just using this dyn constructor and asking Haskell to fill in that representation for that type. Easy. What about fromDyn? Okay, so how does fromDyn work? Well, here's something that doesn't work. That's why it's in red. Right, so this code is what we want to write, but it doesn't type check. Right? What do we want to do? I mean, intuitively, you want to find out whether this dynamic value, right, has that type representation. Right? So inside the dynamic value, we have the representation of some type B. We want an A. And so really what we should be doing is saying, are they the same type representation? If they are representing the same type, they're equal, then this value x, right, A and B are the same, so we should be able to return it. Otherwise, our dynamic type test should fail. But this code doesn't type check for two reasons, right? So the first of all is that equality, right, when we use double equals, it requires its arguments to have the same type, right? But RA is a representation of type A, RB is a representation of type B. We can't even ask whether they're equal or not. And then the other problem is, even if we could ask that, then what, right? We want to return just X. But just X, what type does it have? Right? X is a B, so just X is maybe B. We need to return maybe A, right? So it has the wrong type there. Right? So we can't write this code. Right? So what do we have to do? Clearly unsafe course, right? Clearly. No, let's do better. Okay, I'm done. No. No. Let's make sure. So we talked about creating typables, right, and type representations. How can we use type representation? We want to be able to use type representations in informative ways, right, so that we can compare them, right? So let me talk about, so here I'm just reminding you that the normal equals requires its arguments to have the same type. Here is an equals that's just for type representations. I call it ET, the T for type representations, right? But notice that it has different types of arguments, right? Type rep A and type rep B, right? So the ET will allow us to compare two different types and see if they are the same representation. And not only that, ET also gives us, it's not a Boolean here as a result. It gives us something else. It gives us some extra information. And that extra information is, if it succeeds, if A and B are the same, right, what it's going to do is it's going to give us a proof that A and B are the same. So here we have a GADIT. So this is an index data type. It's indexed by 2 arguments. But notice how the constructor, it only has one constructor. And that one constructor says those 2 arguments have to be the same, right? So this is the equality is proven by reflexivity. So if we get something of type A equals B back and we pattern match on it, and we see that we have REFL, that's going to tell the type checker. The only way we could have constructed this equality is if those 2 types match each other, right? So that's going to tell the type checker that A is equal to B. And so what that's going to do is when we go back to our example, it's going to allow us to type check that fromDyn. So let me just kind of show you how that works. So first, before I go to fromDyn, I just want to just demonstrate ET with just this simple little code, right? So here's this function. It has a funny type, right? It says that for any A, I might give it to you. I might give you an A. Now really, if the type that you wanted was int, it will give you 0. Otherwise, it won't give you anything. That's what this function does. And it does it, right, by using eqt, right, by doing this runtime type test. Is the type that you want? Is the type that you're asking for with typable A, right, is that the representation of int? So I'm calling eqt with the representation of the type rep A, and we know that's available because we have the typable constraint, right? So I'm calling it with the representation of the type A, and then I'm also comparing that to the representation of type int. If that succeeds and gives us REFL, so I'm using the maybe monad, where just with the do, every case analysis for these maybes, if it fails, it immediately stops. Otherwise, we can just say pattern match what was there. So if this succeeds, we're going to get REFL. That's going to tell us A is equal to int, and that's going to let us return 0. Even though it has type int, it's going to let us return 0 as an A. All right, so we're using the GADIT pattern matching on the REFL to make the connection between A and int after we've done this dynamic type test. All right, and that's the key for being able to write from Dyn. Right, so back to our example, right? Here was our definition of dynamic. Here we're creating dynamics by adding those type representations. Now this time, right, we can write from Dyn by just pulling out that representation and comparing it to the representation of A using eqt, right? So, and then if eqt succeeds, we get a proof that A is equal to B, and so then we can just return X. X had type B, but that proof that A equals B tells the type checker we can give it back to a context that wants an A. Right? So this is perfectly type sound. The type checker accepts it. Okay, so we have shown, where are we, right? We've shown that we can use type representations, which are very extensible because the compiler just creates them for every type that you need. Right? We've shown that we can use them to implement dynamic. Right? Now, I want to make sure that we can do everything with these type representations that we can do with that other version of dynamic that I just showed you, right? That we have really fully fledged implementation of dynamic here, right? So I want to go back to 2 of the operations that we had on that dynamic with the other implementation, right? So we had Dyn pair that creates a dynamic from some pairs, and we had Dyn first that projects from an argument based on whether it was a pair or not. And look about, can we take what we've just done and implement with that? Right? Okay, so Dyn pair, if you remember, right, what it wants to do is take 2 dynamic values and create a new dynamic value that is the pair of those values. Right? So here's our 2 dynamic values. Right? So the first one has representation R1, value x1. Second one, representation R2, value x2. We want to create a dynamic where the value is the pair of x1 and x2 together. But what representation do we put here? And I kind of want to answer this question in 2 different ways, just to demonstrate some things that you need from these runtime type representations. Right? So the first way is, well, okay, obviously, the representation we need here is a representation of the pair type. Based on R1 and R2, right? And so what we can do it that way is, okay, here's the pair type. This is a representation of the pair type constructor, right? We asked for it. But we need in our library for type representations a way of putting things together, of taking a representation of 2 things and applying the first to the next, right? Because once we have that, right, then we can kind of apply the pair constructor to the first representation and then to the second representation, and that's going to give us that representation of that pair type. Right? So what this is showing is we need not just a way to create ground representations by using just a typable class, but a way of kind of composing representations together. And the Haskell compiler already has to do that, right? It had to be able to figure out, here's how to make the representation of int arrow int. So it needs something like this already. We just need to expose that because sometimes you want to do that manually. What if you didn't want to do that manually? What if you wanted the compiler to assemble the representation of the pair type? Because it knows how to do that. And the instances say, if you want to make the representation of a pair type, you just need the representation of the two components, right? Can we do that? There's another problem that gets in the way, right? Which is, we have those representations as values, not as constraints. What does that mean, right? Well, when we're creating instances, right, you have typable A, typable B. Haskell compiler knows how to make typable A applied to B, right? But if you have a type rep, you got the type rep because you had a typable instance. But you don't necessarily have that typable instance anymore. You might only have that type rep, right? What can you do about it, right? Well, this is like a special case, right? We know that for this class, there's only one possible dictionary for this class. There's only one possible way you could have gotten a type rep, right? Because it's all built in to Haskell, right? Because GHC must generate these instances. You're not allowed to even write them yourself. Like if you could write them yourself, you could do all sorts of damage, right? And so, but since we know that they're all generated, right? All the instances are generated. We can expose a function that allows you to promote this type representation into a constraint, right? To provide this, it's kind of like an explicit dictionary. And in general, there's a lot of people would like to have explicit dictionaries, but you have to worry about coherence because there might be multiple dictionaries for the same type. But we know, we have this guarantee that there's only one representation for a type. There must only be one representation for a type. So in this case, we don't have to worry about that coherence problem. We know that the only way we can satisfy this typable constraint is having any type rep. And the one we have is good enough, right? And so what does that do in this example, right? We can use with typable for R1 and R2. That gives us constraints for typable A and typable B, and then Haskell can put those together to create the type representation automatically for the pair type. Right, so this is kind of a neat thing that you can do just with this specific class. Okay, let's think about the other way. Right, what about taking these dynamics apart? Right, so here's one way we could do it, right? So this type checks, right? So we want to take a dynamic value, see if it's a pair, and if it is, project the first component format, right? So how do we do that? We can look at the type representation that's with that value, right? And we can compare it against the representation of dynamic paired with dynamic, and if that succeeds, we know that X has type dynamic paired with dynamic, and so then we can just project out that first component, right? And even wrap it up if we want. But what happens, right? It's a little weird, right? Because we don't get the behavior maybe that we want, right? What happens if we do this code where we create a dynamic with two dyne, and it's a pair, right? And then we say, okay, give me the first component of that pair, right? But this dynamic check, this eq_t, is not even going to succeed in this example because the type representation that goes with this pair is not dynamic paired with dynamic. It's char paired with char. And those aren't the same types. And so that test is just going to fail. Right? So we may not get the answer that we expect. Right? So what if we want to write a function that does a type check, but it doesn't do a type check against a ground type? The question that we want to ask is this a pair type? I don't care what the components of the pair are, but just tell me whether it's a pair type so then I can project from it. Because I can project from anything, right? It doesn't have to be dynamic paired with dynamic for me to project from it. If it's char paired with char, I could still project from it. So let me do that. Right? So how can we do that? Okay, well, we're going to need something else from typable. Right? We're going to need something in typable that's going to allow us to kind of decompose our type representations. Kind of like pattern matching for those type representations. Now, typable is this abstract thing, so we can't really have pattern matching directly, but we can provide a function that can do some pattern matching for us. Right? And so what we're going to do is we're going to have this function that's called SplitApp, and the point of this is to actually look at some type representation and decompose it if possible. So every type that we can represent, they all look the same, right? They're either just a primitive type like int, or there's some primitive type applied to arguments, like arrow applied to int and int, or pair applied to char and char. Right? And so what SplitApp is going to let us do is tell us whether we have a primitive type or we have an application. And if we have an application, it's going to give us the pieces of that application. It's going to tell us what the argument, the representation of the argument of that application is, and the representation, well, of the function, the constructor, and the representation of the argument. And then we pattern match on that result. Right? That will allow us to actually examine the structure of that type. Right? So let me show you how that works in the context of dying first. Right? So again, remember, our goal is to write this function, ask the question, are you a pair type? And if you are, project the first component from it. Right? So we get our dynamics. Right? So we get our dynamic value. And the first thing that we do is we try to do a SplitApp. Right? So we're looking at this RPAB. I called it that because hopefully it's the representation of a pair of A and B. RPAB. Right? And so if we do a SplitApp on that, the representation of a pair is got to be the representation of P applied to A and applied to B. Right? So we could do the first stage, right? And so if that succeeds, we get to a state where we know that X, we don't know what X's type is, but we know its type is some application, right? And then we can do it again on that RPA, right? And find out, well, that PA type, it also was an application of some P applied to some A, right? So we're finding out more information about X's type. Right? And then once we've done that, right, that's kind of the structure of what a pair type looks like. Then we can ask, okay, that first part, that P, our representation of P, is that the representation of the product type constructor? Right? And if it is, then we know that X's type is the product type constructor applied to some A and some B. Right? And we don't really care what A and B are, right? What we were interested in is knowing whether we had a product type, right? And then once we know that X has that product type, right, then we can project from it, right? And we're returning a maybe dynamic. We know since it's a product type, it's a product of A and B. We have the representation of A, so we can stick that into the dynamic that we return. So it works, right? We need this way, we need SplitApp to be able to observe our type representations, right? To be able to, it's like pattern matching on them. Now, those were some, I don't know if you noticed, but there were some really fancy types going by just now. Maybe even more fancy than you realize. So I want to go back, right? So I want to look a little more closely at what we just did. Right? It was pretty fancy, but what did we just do? Right? So we look at app result. This was this gadget that we were using as the result of SplitApp, right? So it gives us that when we get it, we find out that some type is an application. But what's going on here? There is a hidden kind going on, right? So we're going to be introducing A and B Those are new existential types that we introduced when we pattern match on this. But we're also A's kind. Oh, I got the kind swapped. Sorry. A's kind is going to be K1 arrow K, and B's kind is going to be K1. We don't know what kind of argument that A takes and what kind of argument B is. We know they match each other, right? But we don't know exactly what it is. So there was an existential kind behind the scenes, right? Right. So when we pattern match, we're going to find this thing out, right? And then the other thing is, so we do the split app, right? So go back to Dine first. We do that split app, right? We take our PAB, we find out that we can separate it into some PA applied to B, right? The PA has this kind, some K1 arrow star, so it's got to be something you can apply. B has to be something you apply it to, and we know that these are equal, so that's where the existential kinds come into play, right? We do it again, right? Here we know we're building up this larger application for what X is type, so that's going to tell us when we split again, we're going to have P is going to take 2 arguments, right? Where A has a kind that works for the first argument, and B has a kind that works for the second argument. That's really what we're going to find out. But then watch what happens when we do this. Now we're going to do ET with RP, and RP is a representation of P which has this kind. And we're going to compare that against type rep of the product kind. The product kind has star, arrow, star, arrow, star. So we are going to be comparing the representations of 2 things that have different kinds, right? They don't even have this. We don't know whether they're the same types. We don't even know whether the things that we're looking at have the same kinds. But after we do that comparison, when it comes back, we want to know that if it succeeds, not only is P product type, but it has to also resolve what those kinds are too. That those kinds must match up with what the kind of the product type is. All right, so that means we have to go back and look more closely at what's going on with ET and that equality. Right. So, so we had ET, and I wrote down these are the types of what ET is, and it's returning this proof, right? But we have to be careful, right? What are the kinds of A and B? So I'm going to be a little bit more explicit here, right? So A has to be able to have kind 1, and B has to be able to have kind 2. They shouldn't restrict that A and B have the same kind, right? We had to be able to call ET with things with different kinds. And that means that this result that we have, this equality proof, it has to be able to talk about things that may have different kinds, right? So the equality proof, right, has to allow A to have one kind and B to have another kind, right? But we still have the same single constructor for it, reflexivity, that says that you can only prove equality when everything is the same, right? So here, our only constructor for this equality is going to create an equality between A, and then here we know that both of these arguments have the same kind, right? So what that means is this guy right here, it's indexed by types, right? Because pattern matching, it tells us type information, but it's also indexed by kinds, because pattern matching is also telling us about this kind information, right? And this thing right here, this is something that you need GHC 8 to be able to write. Right, so that's something new that's coming out, is the ability to have things like this, kind-indexed GADTs. Now this equality, this is something that is pretty well known in dependently typed programming. So you might recognize it as JME if you've programmed in Coq before, or some other kind of heterogeneous equality. Right? And when you first start out, you're like, okay, here's equality. Why would I ever need to even talk about equality between things that have completely different types? But here's an example of you have to be able to ask the question so that you can find out that they do have the same types, or in this case, kinds. Okay, so Let me just kind of finish up. So I just kind of want to talk about what we just saw, right? So what I was doing is that we were building up our dynamic type, right? And the thing about it was really based on this interface for runtime types, for runtime type checking. And the thing that was important about this interface, right, is that it was a safe interface. Once you had the representation of a type, you never lost that connection. So that when you did ask questions about that type representation, right, you could use that, you could communicate that. If you ask questions with ET or with SplitApp, the answers were reflected in a GADIT, in a type or kind index GADIT, so that the answers that you got back could be reflected back to the type system. And so the type system could verify that you were using the results in a consistent way, right? You wouldn't want to compare the types and then just do the wrong thing, right? Oh, this tells me A is equal to B. You want the type checker to make sure that if you know A is equal to B, that's the only case where you can use those types interchangeably, right? So we saw, and that's what that index argument to type rep is giving us, and then the very flexible types of ET and SplitApp lets us work with those type representations in a safe way, right? Because without that, right, if you have just type representation, actually the current implementation of data dynamic, it uses an unindexed type representation. The type rep is just type rep. It doesn't tell you what kind it is, so it's got unsafe course all over the place. Right, so we can make that a lot safer, right? And we can have some flexibility because we have this kind of nice thing how typable and the type reps interact with each other. Because of the type class mechanism, you often know what types you're working with, right? And so that means as you're working with type representations, you can get the Haskell compiler to even build those representations for you, right? And we had with typable that gives us even more flexibility for going back and forth between implicit and explicit usage of type representations, right? And all of this is a really nice example of some really fancy types where we can use kind polymorphism and heterogeneous equality, these kind index GADITs, for really good purposes. But again, all of this, it's not out yet, so you'll have to wait a little bit to play with it, but because it's really depending on some features that are coming out only now. Okay, so with that, I just want to conclude, and thanks to my collaborators who have been talking about this for quite some time, and also Microsoft for funding GHC and NSF for funding my research. Thank you.
We do have time for a couple of questions.
Maybe I missed it, but what are the type representations like at runtime?
Oh, what are they at runtime? Yeah, so I didn't say that. They have to, it doesn't really matter from the outside perspective, but it has to be something, so what's important about it, right? Every time you ask for the representation of a type, you get the same one, so that when you compare it, it always says yes. And if you have two different types, they have to have different representations. So the representations, they have to take into account, what module the type was declared in, and the name of the type. And it's also useful to be able to have the kind of the type stored in the representation, so you can get access to that as well.
Something.
Yeah, something. Yeah, I mean, it's some kind of fingerprint based on that information.
Sorry, here. On your left.
Okay, but I have two questions, and they're both going to cause trouble, so we can go offline. The first one is you've got, okay, so you said, all right, the kinds may vary, so we have to encode the kind equality as well.
Yeah.
But now that we have star and star, couldn't we have an infinitely varying tower of superkind? So wouldn't it be better to have ref will be recursive?
Okay, so let me show you why we don't have to worry about that, right? Because this is actually written in the star language, right? But for K1 to be a kind, its kind has to be star.
So, okay, so now we...
so it always bottoms out.
Okay, so I see.
Yeah.
And therefore there's just certain things that we won't be able to say, but there are probably things that you would argue we probably won't figure out yet for
Yeah.
some time what they are. Okay.
Yeah, and even I didn't write down, what is the classification of K1 and K2, right? In the star language, you can put stars there. In language that doesn't have star, it's really something called box, but you can't actually write it down.
So the second question would be, the representation has explicit type reps that we have, but there's of course the alternate one where you really do use the existential, so you would just capture the typeable dictionary rather than the type rep that is the result of it.
Yeah.
If we did that, we wouldn't need to go back from the type rep to the dictionary. So the question is, what's the reason for projecting down to the type rep prematurely almost?
So it's one of those things where it's actually hard. I mean, you can do it, right? So you're saying, do we really need with typeable, right?
Why not just have it be typeable A arrow?
Yeah. And the answer is, well, you have to do that everywhere, right? And that gets annoying. So yes, you need it in the definition of dynamic, right? But you also even need it. Here's another example of a place where you need it, right? Because when you do a split app, you're getting information back out, right? If I don't have with typeable, then I don't have a way to promote these to be typeable constraints, right? So I would have to then go add typeable constraints to this, and then often then I need to put in proxies, and the code looks really ugly.
Oh, yeah, right. You could do it with
right?
Okay.
Yeah.
Understood. That's helpful. Thanks.
So, here on your left.
Oh, yeah.
So, does with typeable enable you to remove the typeable constraints on the interface of your ST monad at the very beginning?
No. Well, okay.
You still need typeable.
You would have to pass in the type representation instead. It allows you to replace a implicit argument with an explicit one.
Another question, a bit more open-ended. Yeah. I mean, this definitely looks a lot fancier than the current implementation of typeable, but from the point of view of just very practical programming, what are the advantages of this new implementation?
So really that is the question of how do people use typeable, right? If you use typeable, there is something that's in the current implementation of typeable called SplitApp, right, that you can use to decompose, but that is completely unsafe now, right? It just gives you a whole bunch of type representations, but there's no connection between that structure of the type, right? And so if you're using stuff like that, and also...
So if you're introspecting within the structure of dynamics and kind of splitting them into multiple sub-dynamics, that's when it becomes...
Yeah, exactly.
Makes sense. Thanks.
Okay, a question. now that typables are polykined, can they basically replace singleton?
So typables essentially are singletons for types. Yeah. Maybe you're asking for what about things that don't look like types, like
data kinds.
Yeah, data kinds, like a singleton for nats. That's a really good idea. We haven't really thought about merging those together. Mainly because we've been more focused on getting rid of singletons altogether, right? By having something more like a pi type.
Okay.
All right. I think we're going to take a very brief break and then come back for the next speaker. So everyone give your thanks to Stephanie.